Dear students, in the last video we obtained the equation of electrostatic potential due to the dipole. Recalling that equation, see what was the equation? V equal to K into P divided by this R square into cos theta. Right? So P is the dipole moment and theta is the angle between P vector and R. See the diagram first of all. Suppose we are having the plus Q charge over here and we are having negative charge over here. Right? These two charges are separated by some distance 2a and this is the center of the dipole. We get a P point over here. So distance of P point from the charge that was R1, from the O that is R, and from the minus Q charge that is R2, that we have studied. See what is the direction of dipole moment. Direction of dipole moment is from negative to positive. So in this direction the dipole moment is acting. Right? So the angle between dipole moment P vector and this R vector, this angle is theta and this is the theta. Theta is the angle between P vector and R vector. With the help of this equation, we can conclude the potential due to the dipole varies 1 by R square. Means we can say that electric potential is inversely proportional to the R square. Right? It is due to the dipole. But what we studied, due to the point charge, the potential is inversely proportional to the 1 by R. So this thing we have to keep in mind. This is for dipole and this is for point charge. Right? So this is the some important point regarding the dipole. Now we are going to see that what will happen if the charge part, if the point P, if this P point is kept on the axis of the dipole. Suppose this is the axis of the dipole. This is the axis of dipole. If we keep this P point over here, so angle theta will become 0. Or if we put this P point over here, then what will happen? Angle becomes 180. So we will write the cases if point P is kept on axis of the dipole. Right? So two cases may be there. Theta will be 0 degree and theta will be 180. So equation 1 becomes, put the value of theta equal to 0 degree over here, theta equal to 180 degree over here. So V equal to, we will get Kp divided by R square into cos 0. Here we will put V equal to Kp cos 180 degree divided by R square. Students, cos 0 equal to 1. So we write Kp divided by R square. Here V equal to Kp cos 180 will minus 1. So minus 1 divided by R square. So we can write this is minus 1 means we write minus 1. So here the potential is positive. Here potential is negative. As we studied, potential may positive, potential may negative, but potential is a scalar physical quantity. Right? So here in this way we can say that the potential is negative, potential is positive. If the point P is on the positive side, near the positive charge, the potential will be plus. If we put the P point nearer to the negative charge, so it will becomes negative potential. The value of potential will be negative. Correct? So this was the cases. What will happen if the P point is kept over here? Means on the equator line of the dipole. what will happen if the P point is kept on the equator line of the dipole? So P will be over here, angle becomes 90 degrees. So if case number 2, this is the case number 1, A we can write, this is the B thing we can write. Second case, if point P is kept at equatorial line, then theta equal to 90 degree. So putting the value of theta equal to 90 degree in our equation, V equal to Kp divided by R square cos 90. As we know that cos 90 is 0, so V equal to 0. So what is our conclusion? So potential on the equatorial line is 0. That is our conclusion. So in this way you can solve this MCQ, small questions on the basis of this formula, right? Now we are going to see the next question, our next topic, that is relation between electric potential and electric field. So question may be there on this topic like this: obtain the relation between electric potential and electric field. So before that, finding the relation between electric potential and electric field, we must know the concept of equipotential surface, right? So first of all, we will understand what is equipotential surface. Okay, see here, students, we know that we are having, suppose, plus Q charge. Around the plus Q charge, there is a presence of electrostatic force, electric force, right? In all directions, radially upward. That we know. Due to the charge, there is a presence of electric force, electric field, and potential around this charge. Suppose at a distance 1 centimeter over here from the plus Q charge, this is the source charge we can consider, right? Suppose there is a point A which is at a distance 1 centimeter. So what is the potential of this point that we can calculate? Potential of A point is known as the VA, and VA equal to KQ divided by this R. KQ by R. What is R? R is the distance of A point from the source charge, and that is equal to 1 centimeter, right? Here R is equal to 1 centimeter. R equal to 1 centimeter. Suppose I took another charge on the other side. Suppose we are taking another charge on the another side, that is B. Name of the point is B, and which is also the same distance, R equal to 1 centimeter. The distance R equal to 1 centimeter. What is the potential of that point? VB equal to, again we will write KQ divided by R, and that R equal to 1 centimeter. Hence what we can see that equation 1 and equation 2 both are same. So potential of A point and potential of B point is same. Why? Because they are at the same distance from the plus Q charge. We can take another charge. Suppose here we take C, here we take D. So what is the distance of C point from the plus Q charge? Again same. What is the distance of D point from the plus Q charge? Again same, right? So here we can conclude that the potential of VA, VB, VC and VD is the same. Again VC equal to KQ by R. Again VD equal to KQ by R. All the four equations are having same potential because they are at the same distance from the plus Q charge. If we draw a surface joining A, B, C, D, if we draw an imaginary surface by joining A, B, C, D, right? These points which are at a distance 1 centimeter from the source charge. So we get a one sphere, right? That is the one sphere. We can consider a one football, right? Football. So at the center of the football, inside, right, there is a one charge, and you consider the football, surface of the football. Consider any point on the surface of the football, the potential will be same because the charge is kept at the center and the distance of the point and the charge is same, right? So that football is known as the imaginary surface, right? Imaginary surface. This imaginary surface. Consider. Are you getting me what I am saying? This is the imaginary surface. So what is the importance of this imaginary surface? At all points on this imaginary surface, the potential is same, right? At all points on the imaginary surface, the potential is same. So that's why that imaginary surface is known as the equipotential surface. Equipotential surface. Equi means equal. All the points, suppose all the points have the same potential. Suppose consider any surface, and on that surface, if all points have the same potential, then that surface is known as the equipotential surface. Here we consider a surface which is at a distance 1 centimeter. All the points of the surface are at the same distance from the source charge. So that's why potential of all the points which are on the surface is the same. Potential of all the points is same. So that's why this surface is known as the equipotential surface. So due to a single charge we can get a sphere, right? We can get a sphere. So that imaginary surface will be sphere over here. So on the basis of system of charge we can get different types of shapes of the equipotential surface. Suppose we are having a plane sheet. See, this is the plane sheet, right? This is the plane sheet. And charges are uniformly distributed on the plane sheet. So electric field lines we can draw. Electric field lines are moving away from the sheet, right? So from the sheet, suppose 1 meter distance, at a 1 meter distance, suppose here 1 meter distance over here, 1 meter distance over here. So all the points are at a 1 meter distance from the sheet, right? So here we can draw another sheet, imaginary surface, right? On that, all points have the same potential because they are at the same distance from the plane sheet. So that's why the potential on this surface is the same. So that's why here we can see that it is a equipotential surface. Suppose at a distance 1 centimeter we draw a equipotential surface. What will happen? Suppose at a distance r equal to 2 centimeter. R equal to 2 centimeter we can draw another equipotential surface. So potential of this surface and potential of this surface is different, right? This surface is nearer to the source charge, that's why obviously the potential of this surface will be more as compared to this surface. If the potential of this surface is suppose 5 volt, then the potential of this surface will be less than 5 volt, right? So all the points are at the same distance from the source charge. That's why at all points on this surface, the potential will be same. So that's why this surface, another surface, is also known as the equipotential surface, right? So this is all about the equipotential surface. The electric field lines always pass through the perpendicularly to the equipotential surface, right? Electric field lines always pass perpendicularly to the equipotential surface. The next concept that we are going to see that suppose we are having the P point and suppose here we are having the Q point. As we know that the P point and Q point are on the equipotential surface. Means what? They are at the same distance from the source charge. Hence we can see that potential of P point is Vp, potential of Q point is Vq. The Vp and Vq are same. The potential of P point equal to potential of Q point because they are on the equipotential surface, or also you can see that they are at the same distance from the source charge. That's why the potential of P point and the potential of Q point will be same. Now the question is, what is the work done? What is the work done in carrying a unit positive charge from P to Q? See the question, we are having the plus Q charge and we want to carry this plus Q charge from P to Q. What will be the work done? So we know the formula for work done, W equal to Q into delta V. We want to carry the plus Q charge from P to Q. So we must know the potential difference between the P point and Q point. Solving this is the charge Q kept over here, potential of final point minus potential of initial point, potential difference, potential of final point minus potential of initial point. What is the potential of final point? That is VQ. What is the potential of initial point? That is VP. But we know that the potential of VQ and the potential of VP is same. So difference will be 0. Right? So Q into 0, it becomes 0. So work done in carrying a unit positive charge from P to Q is equal to 0. Right? Work done in carrying a unit positive charge on the potential equipotential surface is always equal to 0. Right? So we are moving towards our next question. It's our question that is obtain the relation between electric potential and electric field. So for this purpose, we require the two equipotential surface. That's why I explained this equipotential surface. So coming back to our main question, we are obtaining the relation between electric field and electric potential. See, it's very simple. Look at the board. Suppose we are having a plus Q charge. Due to the charge, the electric field lines are there in all directions, right? So suppose this is the first equipotential surface. We are giving the name A, and we are having another equipotential surface B. Potential of the first surface is suppose V. Suppose the potential of the first surface is V. B surface having potential V and this surface having the potential V plus dV. Right? The potential of A surface is more as compared to the potential of B surface. Right? We want to carry a work done. We want to carry a plus Q charge from the B surface to A surface perpendicularly. We are taking the plus Q charge from B surface to A surface. So this distance, suppose dl is the distance. Right? That work done we are doing. So that work done, suppose F W equal to, we can write force into F vector into displacement dl vector. dl vector. Right? We will write this dl vector. dl. Right? It is dv. Delta V dv that. Right? Students, what is the force acting on the plus Q charge? The force acting on the plus Q charge will be repulsive, as it is a plus, it is plus. Repulsive force will be acting and displacement is toward the plus Q charge. So angle between F vector and dl vector, that is F vector and dl vector, F into dl cos 180 degree. Angle between them is 180 degree. As we know that cos 180 equal to minus 1, so we write F into dl. Minus 1 means we will write like this. So W equal to F equal to, we will write Q into E minus of Q into E. F equal to Q into E. That we know that. So dl remains as it is. This is the equation number 1. Another way we can do the work, right? So work done, W equal to charge into delta. That is also work done in carrying a unit positive charge from this surface to this surface. Which charge we are carrying? Q is the charge, right? W equal to. What is the potential of final point? That is V plus dV. V plus dV. V plus dV is the potential of final point. What is the potential of initial point? That is V. That is V. Correct? So here this plus V, this minus V get cancelled. So W equal to, we can write Q into D. Q into D. W equal to Q into D. So this is the second equation we obtain. This is also work done. This is also work done. So equating one and two. Equating equation 1 and 2. See, what is the equation 1? Minus of QE into DL equal to Q into D. So here this Q get cancelled. E equal to, right, dV by dl minus of dV by dl. So this is the equation we obtain. This is the relation between, in the form of magnitude also we can write, that is dV by dl in the form of magnitude. So this is the relation between electric field and electric potential, right? So here is the end of this question. Thank you, students.